So we have our test on Chapter 9 next Thursday. I will put together a review today, and I'll post that online, so if you want to watch it over the weekend, you can. So yesterday I started talking about this section, and I thought, I've forgotten how to do this, because it's been, usually I've, kind of, like I said, rushed on to Chapter 10, and so I studied a little bit and put a few extra comments in it. So what we're going to do here is we're going to show two ways to come up with a series representation of this particular function, 1 over 2 minus x. And section 10 actually would use a Taylor series. We've already talked about Taylor series and Taylor polynomials, so I think this is the one that we're most familiar with. This is only works for a limited number of functions, and you'll see which ones they are in just a second. And then the second one is we'll use the technique that's discussed in this section, which is actually to use the results of the geometric series that we learned earlier. So we learned that geometric series converges if the absolute value of r, which is the common ratio, is less than 1, and it equals a over 1 minus s, which I'll spell out here in a sec, at a over 1 minus r. And but let's first just look at using a Taylor series, or in this case, so yeah, just to remind you, the geometric series looks like this. It's a summation from n equals 0 to infinity of a, which is a constant, times r, which is the common ratio raised to the n power. And as long as the absolute value of r is less than 1, then it converges. And it converges to a specific value, which is a over 1 minus r. So that's where we're going to use the second technique to show you get the same answer both ways. It turns out, at least for this case, that this method is a lot easier than using Taylor series. So the specific problem is 1 over 2 minus x, and we're going to let c equal 5, which means we're just going to do, actually that means we're going to center it around x equals 5. So we can center the series around any number. If you center it around c equals 0, then it's a Maclaurin series. So this is a Taylor series because we're going to center it around, we're going to evaluate the derivatives at x equals 5. So I put it in the form 2 minus x to the minus 1 so I could just take the derivative and use the chain rule. So what happens is pretty much the sign changes from one derivative to the next because of the negative x inside the parentheses. So what we do is the derivative is you take the exponent, multiply by the argument to the exponent minus 1, and then you multiply it by the derivative of the argument. That's the chain rule. So that's where you get the negative sign. Well, no, actually that's not true. There's actually two negatives here. So there should be a negative from this, and I didn't have it in here, so let me put it in here. So you also have a negative 1. That's the derivative of 2 minus x. So you end up with plus 1 over 2 minus x squared. Okay, now when I take the derivative, I'm realizing I did it wrong last time. So no, actually what happens is every time you take the derivative, each derivative you take, you're gonna get a negative sign from the exponent, and you're gonna get a negative sign from the negative x that's in the argument. So instead of me writing out negative 1 in front and negative 1 in the back, I'm just going to keep taking the derivative, and I'm going to imply that's happening. So they'll all have positive signs because of those two factors that cancel out the negatives. So So when I take the second derivative, I'll get -2 and also get a -1, which gives me +2. Okay, and then I simplify it. It's 2 over 2 minus x cubed by moving this to the denominator. So the third derivative, I take, and I noticed that one's got the wrong sign here. I'm not doing very well on this one. I didn't look at that one. Maybe it's on the next page. Maybe I was going to do it. Yeah, okay. That's probably why I hit it, because it was wrong. But so let me just move to the next page. Okay, so the same kind of thing applies. Every time you take the derivative, you get an extra term from the previous exponent. So here we had -2 is this term, which cancels out with the -1 from here, and so you get 2 as the numerator. When you take the next derivative, what happens is, what's going to happen in each subsequent term is you're going to get an additional factor associated with the exponent. So 3 times 2 is 6. The next one will be 4 times 6, which is 24. Let's just put one more in here. So the fifth derivative will be 24 times 5, which is 120. So we'll have 120 over 2 minus x to the 6. So I've just established this pattern. So the next one would be 720 divided by 2 minus x to the 7th power. And then when you do a Taylor series, you evaluate the derivative at the value of x where you're centering this function around. So if I look at these different expressions and I plug in 5, so I'll have 1 over 2 minus 5, which is 1 over -3, which is -1/3. The next argument is 1 over 2 minus 5 squared. So 2 minus 5 is -3. -3 squared is +9. Next one, you'll have 2 over 2 minus 3 cubed, which is 27, -27. So I get -2 over 27. Here I'll get -3 to the 4th, which is +81. So I get 6 over 81. And then the fourth derivative is 24 over -3 to the 5th power, which is -243. So those are the values of the function and its derivatives at the value that we're centering this series around. So then you plug it in. So another way of writing this is that these numerators are factorial. So this is 3 factorial, this is 4 factorial, 5 factorial. So instead of writing it with just the integers in the numerator, I'm going to write those integers as factorials. So 6 becomes 3 factorial, 24 becomes 4 factorial. If I wanted to take, the next derivative, the 5th derivative, evaluated at 5, I'd have +5 factorial over 3 to the next power, whatever that one is. 3 to the, so what is that? That's, I don't know what it is. Let me get my calculator out. 3 times 243. 729 maybe? Let's try that. I don't think that's right. So 243 times 3, 729. So it is 729. Okay. So those are the values of the derivative at x equals 5. So now what we can do is we put it into the Taylor series. So remember, let me just write that out again because you may have forgotten. But the Taylor series says you take f of c and then you add f prime of c divided f prime of c divided by 2 factorial times x minus c. So that's f prime. And then you have the next term, which is f double prime of c times x minus c divided by 3 factorial. Is that right? I'm not sure if I might have started too early here. Hold on just a second. Let me look. Taylor series, there we go. Yeah, I did start too early. So we're going to, we don't start dividing by factorial to the next term. Then you take the third derivative evaluated at x equals c times x, this be squared, x minus c cubed over 3 factorial. Yeah, I guess the exponent corresponds to the factorial. And then you take the value of the function, the fourth derivative of the function times x minus c to the fourth power over 4 factorial. And you keep doing that. So that's the Taylor polynomial for a function. So if we plug in what we have from our previous step, the value of the function at x equals c was negative 1/3. The first derivative was 1/9. So you take 1/9 multiplied by x minus 5, which is c. The third term is the next coefficient, which was negative 2 factorial over 27 times x minus 5 squared divided by 2 factorial. So negative 2 factorial over 27 is the value of the second derivative. So that's this part. You multiply x minus 5 squared divided by 2 factorial. The third term, the third value of the third derivative was equal to 3 factorial over 81. Then you multiply by x minus 5 cubed over 3 factorial. Then the fourth derivative is negative 4 factorial over 243 times x minus 5 to the fourth over 4 factorial. And so you can see the factorials cancel out. So this factorial cancels out with that factorial, and that cancels out with that factorial. So ultimately, what you end up with is this series, negative 1/3 plus 1/9 times x minus 5 minus 1 over 27 times x minus 5 squared plus 1 over 81. And you can see what this is. This is going to be 3 to the n plus 1 power. So if I take n would be 2, if I try to come up with the equation instead of just listing the terms, so this would be 3 to the n plus 1, where n, so that's 3 cubed. 3 to the n plus 1 would be 3 to the fourth power, and so forth. So you can kind of use some a little bit of inductive reasoning here, and ultimately what you come up with as the expression for the series is that the value of the function, if you take an infinite number of terms, is equal to the summation from n equals 0 to infinity of negative 1/3 raised to the n plus 1 power times x minus 5 to the n. You can see here's 3 to the n plus 1. That was the term that I was just mentioning. You've got to have an alternating sign term, which is the negative 1 to the n plus 1, because you can see how the sign alternates. So you always have to have a negative 1 raised to some power. And to get it to work out so that it's the right time, you raise it to the n plus 1 power instead of to the n. And then you've got this term, which is just x minus 5 to the n power. So that's the equation. So what we did again was let's go back and kind of review what we did here. We took at least 4 derivatives of the original function. We evaluated the derivatives at the value of x, where we want to center this series around. We rewrote it in terms of factorial, ultimately so that when we plugged it into the equation for the Taylor series, that we could simplify it by canceling out these factorial terms. So we got to this version, and then we said, okay, how do we come up with the actual final expression? Well, we looked at it, and we saw this is 3 to the first power, 3 to the second power, 3 to the third power, 3 to the fourth power. We have an alternating situation, so we can kind of figure out what the equation is based on looking at this particular pattern. Okay, so that's reasonably hard. So what we're going to do now is we are going to do the next way. So we're going to, again, use the definition for the geometric power series. And we're calling it a power series because what we're going to do is, instead of the ratio being a constant, the ratio is actually going to be the variable in the equation. And so if we look at the right-hand side of the expression at the top, what the value for the series is, and you compare it with this, the original function that we were trying to find the infinite series representation of, it looks kind of like that. Not exactly like that, but sort of looks like it, because it's a rational expression. And we have two terms in the denominator, and both terms, one's a constant and one's not a constant. So the question is there any way that we can manipulate this to look like that? And darn it, my headphones are beeping, and I didn't bring my cord, so I'm going to have to run over to my office. So let me pause this thing for a second. Okay, so what we're going to do is we are going to try to make this look like that. And I'm going to, so what we could do is we could factor out a -1. So we take the original expression, and if I factor out a -1, I'll have -1 over, actually that looks pretty good, except we don't need to do that. So all we need to do is make this to be 1. So we just need to factor out a half. So if we have if we take this and we factor out a half, we'll have 1 minus x over 2. Is that right? No, it's got to factor out a 2. 2. There we go. That works. So 2 times 1 is 2. 2 times negative x over 2 is x. Or that's equal to 1/2 divided by 1 minus x over 2. So was that the right? Now I'm having questions about the previous one I did around x equals 5. So I think I've got to do something else too. Okay, let me just, I was going to try to do it in my head, but I'm afraid. Yeah, okay, yeah, I was wrong. So it's a little more complicated. What we need to do is we need to make it look something, first we're going to make it look something like this. And the reason I did this, you'll see in a second, it's kind of like when we do partial fractions, or we try to fit a numerator when we were separating terms to make it so that one part was the derivative of the denominator and one part was the part that we solved using the arctangent. So the reason I have to make it x minus 5 is because I'm centering it around x equals 5. If I was centering around x equals 0, it would be a different story. So what I'm trying to do is figure out what a is such that these both are equal to each other. So I just set the denominators is equal to each other. And so you can see the x's cancel out between these two expressions, and I get a is equal to -3. Let's just prove that's true. So if I take 1 over -3 x minus 5, then you'll see in the denominator I'll have -3 minus x plus 5, which is the same as 1 over 2 minus x. So that is the same as that. Okay. Now I have to get it in the form like I was talking about earlier. It has to have a 1 here. So the way to get a 1 from this expression is I'm going to factor out a a 3. Okay, so if I factor out a 3 out of the denominator, I'll have 3. Actually, I'm going to factor out a negative 3. So I'll have negative 3 times 1 plus the quantity x minus 5. And this is divided by 3. So if I multiply it back out again, negative 3 times 1 is negative 3. Negative 3 times x minus 5 over 3 is that. Okay, so these are still equivalent. So this is equivalent to that. And at this point, you can say, oh, that kind of looks like a over 1 minus r, where a is equal to negative 1/3. So this part is the a part, and r is equal to negative x minus 5 over 3. It's because this is 1 minus r, so r has to be equal to negative this value. And then what you can do is you can say, okay, the geometric series said that the summation from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r. So I can go backwards, and I can use the values that I've derived here by making the right-hand side of the equation in a form such as this. So a is negative 1/3, and then you multiply that by r, which is negative x minus 5 over 3 to the n power. So if this is the series, then this is the answer, except again, instead of using r, I'm using something that involves a variable. It's not just a constant, but it's a variable. This is the variable part. Okay, now it doesn't look exactly the same as the one I came up with using the Taylor series, but it will look closer in a second. So we have negative 1/3, and here we have negative 1/3 to the n times x minus 5 to the n. So what I've done is I've taken negative 1/3 and I've broken that separate from the x minus 5. So it's just like ab to the n is the a to the n plus or times b to the n. So I've taken this 1/3 to the n, put it separately, and if I have negative 1/3 to the first power times negative 1/3 to the n, then the final answer is negative 1/3 to the n plus 1 times x minus 5 to the n. So that's what I would deduce is the expression for the infinite series to represent my original function based on using the geometric series technique. And if I go back to finding out the expression that I had when I used the Taylor series expansion, I get exactly the same answer. Okay? So that's pretty cool. So even though I don't think it's used that much, I think it's only limited to a small number of functions that you can use this geometric series method. The Taylor series or the Maclaurin series method, which is in section 10, is much more a general approach. It takes more time to do that because I had to take 5 derivatives and evaluate the derivatives at the value and so forth. Here, I just had to do a little bit of algebra manipulation to take the original expression and fit it into the form where I have a over 1 minus r. And then I can go backwards from the right-hand side of the expression to the left-hand side of the expression to figure out what the actual infinite series representation is. Okay, let me save that for a second. Now there is a you can use that same procedure for deriving the infinite series representation for the arctangent. And you could also use the Taylor series method. We did that for the arcsine the other day, I think, didn't we? Yeah, we did it for the arcsine. But you can also do it for the arctangent. But I'm going to show you how you can use this same method, the geometric series method, to come up with the infinite series representation for the arctangent. So one of the examples they give in the book is this function 1 over 1 plus x. It's similar to the one we just did. We just had one that was 1 over, what was it, 2 minus x or something like that. So to make this into the form like we needed before, which was a over 1 minus r, all we have to do is change 1 plus x to 1 minus a negative x. As a consequence, it is this, in this case, a is 1 and r is negative x. So we can take this rational function and write it as an infinite series, infinite geometric series, by substituting 1 for a and negative x for r. And again, you can take negative 1 to the n out of this expression and make it separate, so it's an alternating sign type result, and then you have just positive x to the n left over. Okay, so that's what you get if you do that. So if you want to look at this expression, which is 1 over 1 plus x squared, which looks kind of similar to that, similar to 1 over 1 plus x, this is the same as this function, except instead of having x, you have x squared. So I'm substituting x squared for x. So I can also substitute here in the infinite series representation, instead of having x, I can put in x squared. So instead of x to the n, it's x squared to the n. And if I use the properties of exponents, x squared to the n is just x to the 2n. Now we know from calculus that the integral of 1 over 1 plus x squared dx is equal to the arctangent of x plus c. So if you want to solve for the arctangent of x, that's equal to this integral. I said plus c, but really I subtracted c, and then I said, well, I like plus c, so I'm just going to change the sign, so don't get confused about that. It's just an arbitrary constant, so I can. And what you do is for 1 over 1 plus x squared dx, you put in the infinite series representation of that into the integral. And I forgot my plus c here. So for this expression, I put in this expression. Now, this is kind of a weird, we haven't really seen that before. How do you handle the integral that involves an infinite series? Well, this doesn't involve x, so this just comes outside the integral. The summation doesn't get affected. The only thing that gets affected is the term that involves x. And we treat n as just a constant relative to the integration. So this is just like any x to the n type integration. We'd add 1 to the exponent divided by the new exponent. So when you integrate this term remains unchanged. The summation remains unchanged. You take this expression, you add 1 to the exponent, and divide by the new exponent. And therefore, the infinite series representation of the arctangent of x is this, and that's what it's in the book. Okay, so it's kind of, there's a couple of kind of cool things that go on in here, and this is probably beyond what I'm really expecting you to do by yourself, but there's two things that come out of this. One is if you come up with an infinite series representation of x, something involving x, you can just put in whatever other expression you have, in this case x squared, you can just plug that into the infinite series directly. So instead of having x to the n, we had x squared to the n. So if I had x cubed if I had 1 over 1 plus x cubed, that would be equal to the summation from n equals 0 to infinity of negative 1 to the n times x cubed to the n power. And then the second thing is if you do integrations where you replace the function with the infinite series, when you integrate that, you just have to integrate the infinite series part as if you were just doing simple polynomial integration, because the power series is always x raised to some n power. Plug this thing back up again. And I was thinking, I haven't done this. I was thinking about it last night or in the shower this morning or something. I'm not sure when it was, but I thought I'd try this idea. So if we look at, we know that the integral of the cosine is the sine. So I thought it might be interesting to take the infinite series representation of the cosine in summation form. So the cosine of x is equal to the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. So I know that the integral of the cosine of x dx is equal to the sine of x plus c. And what happened to the arbitrary constant c? It turns out that if you evaluate this series at x equals 0, you'll end up finding out that c is equal to 0. So that I didn't just ignore, I did forget about it, but there are ways of evaluating c. So that would seem like what I could do is I could say the sine of x is equal to the integral of the cosine of x dx. Again, I'd move c to the other side, but I'd change the sign to make it back to c. And for the cosine, I put in this series representation of the cosine, which is negative 1 to the n times x to the 2n over 2n factorial dx. So when I integrate this, the summation comes outside of the integral. We don't have to worry about that. The negative 1 to the n doesn't change. So you end up with x to the 2n plus 1 divided by 2n factorial times 2n plus 1 plus c. So all I've done is, disconnect myself again. What I've done is I have taken the original polynomial, the term that involves x, and I've added 1 to the exponent, and I've divided by the new exponent. And so the infinite series representation of the sine should equal that, and I don't know if it does, so let's write it. I'm going to look in the book and see what it says. And if it doesn't, we may have to it may be that I need to make a slight algebra thing. So if it doesn't, I'll have to figure out why later, because I haven't actually done this in real life. But if you look at the book, the sine is equal to negative 1, the summation, sorry, I've got to put my summation sign in here. Summation from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. So the only difference between what I found in the book and what I derived by integrating the series representation of the cosine is this part, but 2n plus 1 factorial is going to be equal to 2n plus 1 times 2n factorial. which is that's what I have. So they are the same. This can be combined into that. So it actually does work. Woohoo! I'm going to save that. Okay, so let's go back to section 9 here again. We'll do another, see if I got another problem to work through. Okay, so here's another one. So we have the function is 1 over 2x minus 5. We're going to center it at c equals -3. So the first thing I do is I just factor out a -1 so that I have constant minus the term that involves x. And then I do the same thing that I did just a minute ago. I say I want to set this equal to an additional fraction that fits into the form of the geometric series better. So what I'm trying to do is have -1 over a minus 2 times x plus 3. And the reason I chose x plus 3 is because I'm centering it around c equals -3. So whatever this c value is, you need for this to be x minus this value. So if I want to make these denominators the same, so they're equivalent to each other, I say 5 minus 2x equals a minus 2 times x plus 3. And again, the x parts cancel out. -2x, -2x, so I'm left with 5. And over here I'm left with a and -6. And so a is equal to -11. So my original function that I'm trying to find the corresponding infinite series is going to be equal to -1 divided by -11 minus 2 times x plus 3. So those are equivalent to each other. And then finally what I have to do is factor out 11, or -11 I guess. So I'm going to factor out -11 in the denominator. So that'll be 1 plus 2 over 11 times x plus 3. So that's the denominator. And the numerator I have -1. The negatives cancel out, so it's really 1/11 divided by 1. And what I have is a minus, so it's minus 2/11. Again, all this algebra is just to get into the form of a over 1 minus r. So this is not a over 1 minus r. This is a over 1 minus r.
Shouldn't it be a equals 11 if you're in 6 to both sides?
Oh, positive 11. You're right. Thank you. So let's fix that. That's positive 11. Okay, so I don't have to do that. That becomes negative. So that's going to already be okay. And that's negative, right? Just double check it. Everybody okay with that? Well, we'll find out because I did it previously. Okay, so we got -1/11 over 1 minus, yep, okay. So what that does is implies that a is -1/11 and r is 2/11 times x plus 3. So now you can just go back and you can plug that into the relationship where, you know, we've got a over, well, we've got a over 1 minus r is equal to the summation from n equals 0 to infinity of a, which is -1/11, times r, which is 2/11 times x plus 3 raised to the n power. And you can take this out and combine this term with this term, and you'll get 2 to the n. So here's 2 to the n. you'll have 11 times 11, well, 1/11 times 1/11 to the n power, which is 1/11 to the n plus 1 power. You can factor out the negative sign. So there's no alternating nature to this. They're all negative. So 2 to the n, 1/11 times 1/11 to the n power is 1/11 to the n plus 1, and you have that by yourself. And it converges when r is less than 1, which means this has to be less than 1. So I don't know if that's on the next page or not. Yeah. So the actual interval of convergence, we use the convergence criteria for the geometric series, which is the absolute value of r has to be less than 1 for convergence. So we take the value of r that we came up with to make this whole thing work out. If you multiply both sides by 11, divide both sides by 2, change the absolute value into this kind of inequality, and then subtract 3 from every term, you end up with that this series representation of this function converges between -17/2 and +5/2. So we hadn't done that before, but that's how you determine the interval of convergence, by using the convergence criteria for a geometric series. And I think I'm not sure what you do about the endpoints. I think there is a way of doing it. I think you just evaluate this at the endpoints and then use whatever test is appropriate. So I'm going to assign the homework for this section here. There's just 3 problems. So again, what we did was, because the geometric series has convergence criteria, and you can actually have an expression for what the value of the series converges to, you can use that to try to fit functions which don't have a fixed ratio, but the ratio depends on x, to work your way backwards through the whole convergence criteria and the evaluation of the actual value of the series to imply what the series representation for that original function is. It's somewhat limited to things like the functions that we've seen. Now you can stretch it a little bit like we did with the arctangent where we took the integral. So there are things that allow you to make it a little more flexible, but things like the sine or the cosine or e to the x, you really can't use this technique. It's really only used for ones that look kind of like what we've done so far, or the integrals can be used that way. So like I said, in the past I haven't even covered this, so this is something new. Let me just show you one last thing here. Just another, well, we already did that one. We did this one so that we could solve the arctangent problem. So what else have we got here? Yeah, let me look over this for a second. Oh, okay, yeah. Well, I'm going to use another example just to show you where you might use this again. If you had, if you wanted to find the infinite series representation of something like x squared minus 2x plus well, no, that's not what I want to do. Minus 3. So I'm trying to find the infinite series representation. And again, I could use Taylor series to do this. I could take the derivative, multiple derivatives. But what you could do is you could use partial fractions to rewrite this by factoring the denominator. So if I factor the denominator, I'll have x minus 3 times x plus 1. And then I would break that into two series, or two terms, like this. And you can see that after I've broken them up into individual linear terms, once I've broken them up into individual terms that have a linear part and a constant part, you can imagine how I could manipulate those to fit into the geometric series type arrangement, a over 1 minus r. So I just have to divide. I'd find out what a is and b is, and then I could just factor out a -1 to make it 3 minus x instead of x minus 3. And then I could divide by 3 to get, so it's 1 minus x over 3. And then I could, and you could do that for each term. And then you could come out with a series representation. It would actually be two series, one that would involve the x minus 3 thing. And also it depends upon what value of x you want to center this around. So we haven't specified that. But again, hopefully you can see how the original one doesn't fit into what we've been learning this particular case, this particular section. But we can see that once you apply partial fractions, we get something that kind of looks like that. And so you can probably imagine that, hey, I could do that, and I could end up with the summation involving this part and the summation involving that part, and the total series representation would be just the addition of those two infinite series. Okay, so that's it for today.